I'd now like to invite Dr. Brendan Smith, who will be talking about his project, Cheap, Robust Nano-Filtration Membranes for Household Water Treatment.
Okay, well, thank you very much for staying until the end of the session here. I know it's been a long 2 days, so I really appreciate it, and it's great to be here. As was mentioned, my name is Brendan Smith. I'm a current postdoctoral associate at MIT in the Department of Materials Science Engineering. I'm working in the group of Professor Jeffrey Grossman, but the team is actually a fair bit larger than that. We also have currently Lily Cheng-Zedler of the MIT Sloan School of Business, who's doing a lot of the business development for our team right now. Rahul Ramakrishnan is a junior undergraduate at MIT in our department, has been working a lot on the technical side of the project, which you'll see in these slides here. And then finally, Dr. Jason Propus, who's with the MIT Tata Center, has been really instrumental in connecting us to the Indian market, not just in arsenic filtration, as I'll speak to here, but also to a number of other industries as well we're exploring during this visit. So I'd like to start with a bit of brief motivation. Why are we pursuing this project in household water treatment? I think we're all aware that there is a major issue in the Indian drinking water space. So about 150 million Indians currently lacking access to safe drinking water. And of course, it's not just an Indian problem, it's a problem all around the globe today that we're facing, very severe. And so when we think about safe drinking water, you probably likely come to mind with bacterial and viral contamination, among other things. Of course, this is a massive issue. The majority of that 150 million does constitute this bacterial contamination. However, about 50 million, or a third of that number, is something a bit more insidious, and more specifically, this is arsenic contamination. And so arsenic is something that is much smaller in terms of actual physical size, something that's much harder to detect in the water supply, and something that's much harder to remove. And what's even more, this will actually accumulate in someone's body for many years or even decades before the effects of this contamination are actually felt. And so this results in things like cancer 10 or 20 years down the line when it's already too late to do anything about this. And so we're addressing this issue. In Bangladesh, it's about 70 million people being affected by arsenic. In China, it's about the same, and then also pretty rampant in South America and even some parts of North America. So really, truly a global issue. And so we have many available techniques for treating water, of course. And so really to understand why we're not doing as much as we can in the arsenic space right now, we have to look at the current landscape. And this is, of course, something that's constantly being adapted, and new solutions are always being brought to market. And so I'd love to hear from anyone who knows of anything more recent that we haven't mapped out here. This is just a very vague kind of conceptual understanding of the landscape so far. And so if we look, I would really lump these into three main buckets. The first being chemical treatment. So this could include something like the addition of chemicals to 10 or 20 liters of water you'd like to drink in a household. This will then cause what we call flocculation, or clumping together of that arsenic into much larger flocks or clumps. You can actually easily filter these out within about half an hour through a cloth filter, for instance, or even a piece of clothing, something very simple. And now, while this has been shown to be very effective, there was a very interesting trial run, I think about 5 or 10 years ago, where about 100 million of these little sachets of chemical powder were distributed all around India and other countries in Southeast Asia. And while it works very well, there was actually really no demand for the repeated distribution of these sachets. And it was kind of determined that the reason for this is because it's too labor intensive. Even though it's extremely cheap and it works very well for arsenic removal as well as some of these other contaminants here, what you have to do is first open the sachet, dump it into about 10 liters of water, mix it up, wait for half an hour to an hour, and then filter it through this cloth filter. And so it's determined that even that relatively simple amount of labor is actually too much for people to really want to undertake in order to achieve clean drinking water. And so it turns out not just to be the cost and the efficacy of the solution, it also has to fit with the lifestyle of those people who are using it, which sounds fairly obvious, but when you get into these different solutions, it becomes more and more evident how important this really can be. And so the second bucket I'd like to speak to is sand filters, but more so absorption technologies. So there's been a recent push, I'd say in the last 10 years, to use iron oxide to actually absorb the arsenic from water. This works very, very well, and there's been, I think, 5 to 10 different iterations on this over the past few years. One thing where it falls a little bit short is in the virus removal. And so bacteria can be dealt with as well as arsenic through this iron oxide absorbance, but the viruses are still quite small and not really absorbed in the same mechanism as the arsenic, and so that's difficult. And also here, in this very important category we're finding of the upkeep required, there is some changing out of the media every year or two once the iron oxide is saturated, either switching out altogether or regeneration through some type of more complex chemical treatment. And so we'd like to still do a little bit better in terms of how much upkeep we can decrease here, as well as being more effective in the viral removal category to have more of a blanket solution. And so the last bucket I'd like to speak to, and where we're really working on in our work, is the filtration side. And so you're probably aware in many areas around India, there's been these water ATMs by Piramal distributed. And these are RO, or reverse osmosis filtration membranes, cleaning this water to really what's the gold standard. When you have bottled water, that's how it's all produced through reverse osmosis. And so this is really the global industrial and also drinking water golden standard. The real downside here, while it's extremely effective in all these categories, and while the upkeep may be low for the individual person, the upkeep is actually very high in terms of these centralized stations. You need to do a lot of membrane replacement, backflushing of the membranes, cleaning of the membranes, and in some of these more remote locations, these water ATMs have fallen out of use within a year or two just based on this extremely high upkeep requirement. And so what we really like to do is obtain the efficacy of the RO while drastically reducing this upkeep and also, if possible, reducing this cost. And so the solution that we've arrived at to do this, developed over the last 4 or 5 years in our lab at MIT, is a silicon nano-filtration membrane. I'll speak a bit to how we actually make this on the next slide or two. But basically the main benefits of this we really see are, number one, it's extremely robust and durable. And that means that we can actually run this in a system with very little maintenance over very long periods of time. And of course, all membranes will foul and deteriorate over periods of time, but we'd like to extend this 5 to 10 times longer than you can use an RO membrane for before any kind of cleaning or maintenance is necessary. And replacement should really never be necessary due to the intrinsic robustness of our silicon material here. Secondly, silicon is the second most earth-abundant element that we have today, and there's a vast amount of processing knowledge through the semiconductor industry, of course, and so very easily to work with these membranes, and that really leads into the third point, which is that we can actually come up with a very scalable and rapid manufacturing technique to produce these novel form factors of membranes. In terms of performance, we've been really focusing on arsenic 5 or arsenate in water right now, and it's a bit easier to remove than the alternative arsenic 3 based on the charge and the size. And so before using actual arsenate, we focused on this molecular dye, which is of very similar molecular weight and also molecular negative charge. This allows us to do much more simplified and safe testing as an analog to arsenate before going over to arsenate itself. And with this dye, we're able to reject up to about 92% of dye from the feed stream to the permeate going through our membrane from top to bottom. And transferring over to arsenate very recently, we've noticed it's a very good analog for, the dye is a very good analog for arsenate rejection. And so we can expect about a 90% rejection of arsenate once we're able to do more testing, which is fairly promising. So in terms of how we actually make this, there's three very simple steps. And we're actually moving now to only 2 steps without this first thinning step that's involved. We basically take off-the-shelf silicon. We use a chemical wet etch to thin the silicon down to a point where white light can actually transmit through the silicon, comes out as rather yellow or orange. The second simple step is a industrial metal sputtering process in which we deposit these metal catalyst particles on the surface. It takes about 2 seconds to deposit those. We're essentially spraying these droplets of metal onto the surface. And the third step is a second chemical etching step, whereby these metal catalysts actually act as drill bits on the nanoscale to etch down from the top to the bottom of this silicon chip or wafer and actually produce our membrane. And so in this cross section here, if we were to cut this membrane in half and look from the side, we're about the thickness, a fifth of a human hair in terms of thickness here from top to bottom. And these metal catalysts actually transit from this surface here where they're deposited, and they drill down based on this chemical etching process to the other side. And that actually forms those water channels through which water can travel, but which are actually too small and too highly charged for arsenic to enter the channel. So that's the mechanism of rejection there. If we go back to our initial landscape and really place this in the context here, we think we can achieve similar efficacy to reverse osmosis, not in terms of desalination, but that's not something that's really required in a lot of these areas. It's simply arsenic rejection. So we think we can achieve similar efficacy in terms of arsenic, viral, and bacterial removal. We think we can also drastically reduce the upkeep required in terms of the anti-fouling ability of the membrane and resiliency over long periods of time, 5 or 10 or 20 years. And we also think that we can do this for about 1/10 of the cost of a water ATM, for instance. And so we're pretty excited about moving towards the piloting stage for this, and we can talk a bit about, after this discussion, what are our next steps for that as well. So more along those lines, we kind of foresee this as potentially 2 different implementation strategies. One is where we could install this membrane setup, very small module, directly at the site of the bore well. This could potentially provide clean water, arsenic-free water, bacteria-free water, viral-free water for potentially up to 5 families of 5 people or so, or 4 people. And the advantages of this are we have a relatively small capacity. We're almost at the point now where we could actually implement this based on what we've achieved in terms of scalability. And you also here have a sense of ownership and pride that you're actually owning this device at the site of the bore well, and not really experiencing much of a lifestyle change in that process. On the other side, we could look at the community scale, where we serve about 50 households. The advantages of this are we could explore more feasible financing, much like the water ATMs with Pier Mall, and we could also have centralized maintenance that comes with. So of course, we're very focused on this arsenic issue, but we also recognize that there are a lot of advantages to having membrane technology, which is extremely resilient, operable over long periods of time, and has a bunch of other benefits I didn't really speak to today, including the ability to deal with highly concentrated effluents, very acidic and basic waste streams, organic solvents, and many more types of very harsh cleaning environments, as well as high temperature. And so we're thinking about that as well, looking during this trip specifically into the dairy, textile, pulp and paper, and oil and gas industries. So we're very excited about any opportunities if you have ideas in those spaces as well. With that, I'd like to thank you for your time, and I'd happily take any questions you might have. Sure, applied, yeah.
And that's for 10 psi pressure.
100 psi.
100.
Yeah. Although it does vary, so currently we're trying to optimize this based on the porosity, pore size, and thickness of the membrane. Yeah, but great question.
Hi, here. How much does it cost to make these devices, and what's the shelf life of these devices?
Right, so the shelf life we can only estimate because we haven't been in the field yet. In the lab, they're perfectly, runnable for as long as we've done it so far, which is a couple of years. So as long as you're able to clean the membrane, no membrane is completely anti-fouling, but we have a very hydrophilic surface, very smooth surface, and extremely inert in many different types of cleaning environments. And so if you do a proper cleaning protocol every week to a month, depending on how harsh the water is you're putting in, you can really easily regenerate that membrane. In terms of you were talking about the cost, and so I didn't include that on here. If you look at a typical ceramic membrane, the cost is about $700 per square meter of membrane surface. And when I'm talking about this, I'm talking about not the very simple ones which are made in the field in terms of the clay pot ceramic, but more so the ones you'd buy which would approach the same molecular cutoff size that we're trying to approach here. And we're about $150 per square meter. So we're about a quarter to a fifth of the cost based on our cost modeling in terms of scalability of what you'd see for ceramic membranes.
So you would regularly need to clean these devices in order to avoid biofilm development, etc.?
Yeah, you would have to do some cleaning. In terms of how often, we have to determine that, and that's why we're really excited about doing some piloting here in the field. And so we don't clean ours in the lab, but we're doing more short-term testing. So we're looking at going to more of a cross-flow. In the lab, we do what's called dead-end filtration. So we put all our water in a chamber, we seal it up, and push it all through the membrane. So that's the worst way in terms of fouling avoidance. Something that's more realistic for the field is to do what's called cross-flow filtration. So you have your membrane here, and you actually flow the water across the surface, generating kind of a shear force that can knock off that foulant to some reasonable degree, and that's going to extend the lifetime of the membrane. But we don't know exactly how often you'd want to clean it to optimize. That might just be adding, say, like a chlorine tablet once every week or once every 2 weeks, for instance, and letting it sit for half an hour.
Thank you.
Thank you. Okay, thank you, everyone.